Hello, Chemistry 1001, Introductory Chemistry 1, self-ionization of water. We're going to talk about that. What did we just complete? We talked about conjugated acids and conjugated bases. We talked about weak acids and strong acids and the definitions of those and identified some of those. So now we're looking at self-ionization of water. Pure water is virtually 100% H2O, but a small amount of it does form hydronium cation and hydroxide anion. And so this is part of the reason why it is amphiphilic and can be an acid or a base, because it can act as an acid or base even in a pure solution. But it's such a tiny amount that it doesn't even conduct electricity. And we're going to look at the values for this. If we take two water molecules and we react them, this arrow is a little bit misleading because this is certainly an equilibrium. It doesn't just go in one direction. So we should have an arrow going back and forth. This arrow is actually really tiny. Very small amounts of water can form an acid, which is a hydronium cation, and very small amounts of water can form a hydroxide anion. It's almost unnoticeable. In fact, the pH is considered 7 for water if it's pure water. The dissociation of water is self-ionization, and it's a very weak electrolyte. Since it's a weak electrolyte, it has to have arrows going in both directions. H3O plus is called the hydronium ion. In pure water at room temperature, hydronium cation is considered a very low concentration, or a molarity of 1.0 times 10 to the negative 7th molar, a very small amount, that's moles per liter. Hydroxide anion is considered to be in a concentration of 1.0 times 10 to the negative 7th molar. That's a very small amount. Indeed. And so we can come up with a equilibrium constant for this, because remember, we cannot use water. We cannot use the concentrations of water in an equilibrium constant. And this is exactly why we don't put those numbers in here. And we just get KEQ equals hydronium cation concentration times the hydroxide anion concentration. So remember, liquids are not included in the equilibrium expression. So water is just too voluminous. There's too much water to put that into the reactant, which would be in the denominator. And it'd be a gigantic number, and it would be almost zero. We'd have no useful information from that. So we ignore this in the writing the equilibrium constant here. It's just the products in the equilibrium constant here. And if you could imagine, we could put hydronium cation concentration in here, and we could put the hydroxide concentration values in here. We multiply that together and we get a special equilibrium value. We're learning that Kw value, which is, if we put those concentrations in there, is 1 times 10 to the negative 14th, a very small amount. It is unitless. Make sure you know how to multiply scientific notation together. Remember, both of these are 1.0. Both of them have equal concentration. So if you take 1.0 times 10 to the negative 17th times 1.0 times 10 to the negative 17th, you can add the exponents. Negative 7 plus a negative 7 gives you negative 14. So review your mathematics if you're unsure. This is unitless. There is no units in the Kw. That gets canceled out. We don't have to worry about how that happens. Just know that it does. So Kw is simply unitless. And Kw doesn't change, by the way. It's a constant, and we can use it as a backdrop for many weak acids and many weak bases. And we're going to see how we do that. Why can we do that? Because water is the gigantic medium, the solvent. There's tons of water, and then whatever we throw in that water, whatever system we create, whether it be acetic acid with vinegar, or whether it be carbonic acid, or it'll be a weak base such as ammonia, it doesn't matter. water is a predominant species, and Kw will be the same. Kw will still equal 1.0 times 10 to the negative 14th, no matter what kind of acid we throw in there, with respect to up to certain concentrations. So it works within, 1 molar range concentrations. It's quite good for small molarities. So we'll see that here. We'll be able to use this to figure out things about the pH scale. And the pH scale, we'll talk more in depth about that, but just know that the range is when something is 0, 1, 2, 3, 4, it is acidic. If it has a high number on the scale, which goes all the way up to 14, say it's 11, 12, 13, or 14, it's very basic. So if it's very acidic, it has a lot of hydronium cations to donate or to react, as opposed to if it's very basic, it has a whole bunch of hydroxide anions in the solution. So this tells us, the pH tells us a lot about the solution. And why is this even important? Because we use this in biological systems all the time. pH is very important to biochemistry, to enzyme activity, and of course one of the overarching ideas is the pH of our bloodstream is around 7.3, 7.4. It's slightly basic. pH scale is similar to the temperature scale, assigning relative values of, it says hot and cold, but in this case it would be acid or base. The pH of a solution is defined as pH equals the negative log of the concentration in molarity. So if we have a calculator, we need a calculator for our tests, right? So don't forget that. You have this calculator, correct? You'll be able to enter scientific notation of these particular values that you might be given and figure out what the pH of the solution is by the given molarity. And let's see how that's done. First, some backdrop on the definition of pH. If you add an acid and you add acid to any solution, you will increase the hydronium cation concentration. Let me switch over to a laser pointer. And so we have if we add acid, we of course will increase the hydronium cation concentration, and the hydroxide concentration will drop. If we add base, the hydronium cation concentration will drop. And at some point, the hydronium cation and the hydroxide concentration can be equal when equal amounts of acid and base are present, and therefore we're going to end up having this situation. And you might say, well, wait a second, Dr. Pryor, if there's equal amount of acid and base, wouldn't they just completely neutralize themselves? Yes, they should. But when it's really, 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 really small amounts of concentration, the hydronium cation and the hydroxide are so dilute, they may not have even a chance to interact. Remember what we learned about concentrations. The higher the concentrations, the more opportunity for a reaction to occur. So neutralization of an acid and base may not occur when it's really dilute because they don't come into contact very much with each other until the concentrations go up. So 1.0 times 10 to the negative 7th concentration is really low. And so these species can exist without running into each other. So let's think about this here. This is wrong here. This should be H3. Oh, that's a typo. So the hydronium concentration in molarity times the hydroxide concentration in molarity in a water solution, in an aqueous solution of acid or base, is 1.0 times 10 to the negative 14th. That's the equilibrium constant of water, which is always, Kw is always this value. That's always Kw. That's not going to change. Remember that in case it's on a test. Now, the pH of solution can be calculated if the concentration of either ion is known. So approximated using indicator pH paper, a color change can tell us the solution of the pH. And so we can use that to give us the pH by just a visualization of color. We can use a pH meter and we can measure electrical properties that will tell us what the pH is. And so we have many ways to measure the pH, but we can use our calculators to figure out if we have a concentration, what that pH value would be, or if we have a pH value, what would the concentration be? Now we have tricks to doing this. These help us But we must remember our facts. Kw, of course, is 1.0 times 10 to the 14th. Switching over to a laser pointer. And so we know that the hydronium and hydroxide concentration in a solution of water in a dilute solution of acid or base is always going to equal this when it's an aqueous solution. And so if we have a pH and it equals a negative log of hydronium cation, we can take the molarity of the hydronium cation and then take the log of that with our calculator. We'll get a negative number and we multiply that by just negative or -1, and we will get the pH value on our scale to measure hydronium concentration, which the lower the value, the higher the hydronium concentration, right? pH of 1 is a more hydronium concentration than a pH of 6, which has less acid, therefore less hydronium concentration. So let's take a look at this. We can use our calculators, but when it's an easy number like 1.0 times 10 to the -4th molar, which is moles per liter of hydrochloric acid, we know that HCl is a strong acid. So we know that this is going to disassociate completely. So we're going to have 1.0 times 10 to the -4th moles per liter or molar of hydronium cation. And so we know 1 mole of HCl produces 1 mole of hydronium cation in solution. And so therefore, this it's just a small error. Somebody, again, we did not get these typos that were made. That should be H3O plus equals 1.0 times 10 to the -4th molar. We plug that into this as the hydronium concentration. We take the log of that, we get -4 times a -1, and we get 4. Since this number is 1, if this number is 1, we just look at this and we know that the log scale is a factor of 10. So a pH of 1 is 10 times stronger in hydronium cation, or 10 times more concentrated in hydronium cation than a solution of pH 2. But we can just call this -4 as 4, and so we can have the pH or close to it. So this is useful. Okay, so calculating, so what is the hydronium cation concentration of a solution of pH 6? So now we have to work backwards. And so we can take the log of, for example, we can make this so we can manipulate this equation, and we can get hydronium cation concentration. And so we take the inverse log of pH, whatever that value is, and we take the inverse log of this negative log, and we end up getting this calculation of where this becomes H3O plus hydronium cation, and we get the pH of 10 to the -pH. So we can get the concentration of the hydronium cation from the pH value. And so this can work both ways. We can, by this equation here, 10 to the negative pH, we can put in a -6 here, and we can get the fact that this is going to be 1.0 times 10 to the -6 molar. Okay, so we can work backwards as well by taking the inverse log, and the alternative mathematical form of this equation will now get us the hydronium concentration as opposed to the pH, and we can plug in the pH value and get the concentration or the molarity of hydronium cation. So if we have a molarity of 1.0 times 10 to the -3rd molar of potassium hydroxide, what are we dealing with? Well, we're dealing with a base. This is no longer an acid, but this equation will still work for us. We'll still be able to figure out the hydronium cation concentration. Since we know this is going to be dissolved in water, we can use Kw, which we know is 1.0 times 10 to the -14th. And so if we can figure out that we have this much of um, potassium hydroxide, we know we also have this much of the hydroxide solution because it's a strong base and it all dissociates. There is no equilibrium. So we have 1.0 times 10 to the negative third molar of hydroxide. So how can we figure out what the pH is of this? Well, we could do POH, but we don't want to jump that far ahead yet. We want to use what we know. We want to figure out, since we know the hydroxide concentration and we know the Kw of water, we'll be able to figure out what the hydronium concentration is, right? It could be H3O plus, or we can just call it H plus. That's our unknown. It's an algebraic problem, equation. So let's see if we can figure this out. We know Kw is 1.0 times 10 to the negative 14th. That didn't change because we're doing this reaction in water. This acid-base reaction is happening in water. We don't know the hydronium concentration. We do know the hydroxide concentration and the Kw. So we need to just solve for the hydronium cation concentration, which of course is going to be smaller than, and there should be an X here, sorry. It should be 1.0 times 10 to the negative 11th equals the hydronium cation concentration. So that is a lot less than the hydroxide because this is a basic solution. Nevertheless, we can still determine the pH value. We can put in plug this number into the molarity or the concentration of hydronium cation, take the logarithm of that, and in a negative, we'll get a negative 11 times the negative, and we'll get a pH of 11, which isn't acidic at all. It's basic for the most part, which makes sense. We have way more hydroxide anions this time than we have of hydronium cations. Okay, so calculating hydroxide from pH. Let's see what we can do here. We have the hydroxide concentration of a solution. What is that? Knowing that the pH of the solution is 5.0. Let's find the hydronium cation concentration. So we have the hydronium, which equals 10 to the negative pH. We plug in 5. And so we figure out from that the hydronium cation concentration is 1.0 times 10 to the negative fifth. And so using the Kw of water, which we know works for not weak acids and bases, for low concentrated acids or bases, whether they're weak or strong, we could end up using this. But with weak bases and weak acids, we end up using something like Henderson-Hasselbalch equation, which is more Gen Chem level stuff. And so we want to find the hydroxide concentration with the known hydronium cation concentration. So this is just an algebra problem. We set Kw equal to the product of a hydronium concentration times the hydroxide concentration. We put in 1.0 times 10 to the negative fifth for the proton concentration, and we don't know what this is. We need to solve for that. And when we do, we find out that the hydroxide concentration, since the pH is 5, we know that hydronium cation concentration is going to be greater than the hydroxide concentration. That's exactly what we find. It's 1.0 times 10 to the negative 9th. We could have done this since both of these are 1 divided by 1 is 1. And if we divide 10 times 10 to the negative 14th divided by 10 to the negative 5th, we end up subtracting a negative 14 minus a negative 5, which is a plus 5, and we get 9. So we can do that with or without our calculator, but I would definitely learn how to use our calculator, because what happens is when this number isn't 1, it gets a little dicey. And that does it. The second part of Chapter 8. We have more of Chapter 8 coming. Thank you for watching Chemistry 1001 at ULM. You have a great day.